straddling the boiler at 70 miles an hour. The engineer sits alone, vibrating iron beneath his boots. 20 feet back, the fireman shovels anthracite into a furnace he can't see around. They can't hear each other, can't see each other. One man might die, and the other wouldn't know for miles. On more than one occasion, a Camelback engineer perished in the cab while the oblivious fireman continued to stoke the fire. This machine was a marvel of economics and a masterpiece of industrial compromise. It burned the coal nobody wanted and turned anthracite waste into profit. It screamed down passenger lines at speeds that terrified riders and thrilled railroad executives. The Reading Railroad called them Mother Hubbards. The Baltimore and Ohio called them snappers, because when a side rod snapped, it turned the engineer's cab into a coffin. We're going to find out why railroads built nearly 3,000 of these death traps anyway, how they worked when nothing should have, and what it cost the men who rode them. How an engineer could die and the fireman wouldn't know for miles. How cheap coal became more valuable than human life, and why it took 50 years to admit what everyone already knew. This design was killing people. Mountains of waste eastern Pennsylvania, 1870s. If you stood anywhere near the anthracite coal fields, you'd see them. Black mountains of culm, coal dust, and fragments too small to sell. 20% of every ton mined was waste, piled high at the mines. Worth nothing. Burned nothing like the chunks sold for home heating. The anthracite industry had a problem. They were sitting on mountains of fuel they couldn't use. Culm, the leftover fragments from mining and processing, accumulated faster than they could get rid of it. Small mountains of black waste growing taller every year. And it represented almost 20% of total production. 20% of their product was garbage, and John E. Wooten stood looking at those piles like they were mountains of money. Wooten had worked his way up through the Philadelphia and Reading Railroad. Started as an apprentice at Baldwin Locomotive Works in his youth. 8 years of grease and steam and iron, learning how pistons drove rods, how fireboxes generated steam, how every component had to work in harmony, or the whole machine would tear itself apart. By 1866, at age 36, he was superintendent of motive power for the Reading. 10 years later, in 1876, he became general manager of the entire system, and he had a problem that was also an opportunity. All that worthless culm just sitting there while his railroad paid good money for quality anthracite coal. The Reading hauled coal, it was their business, but they also burned it to move their trains. Fuel costs were bleeding them. Every locomotive needed tons of quality coal per day. But those waste piles, if he could find a way to burn culm, the savings would be astronomical. The problem was physics. You couldn't just shovel culm into a normal locomotive firebox. Anthracite burns slow, hot, clean, but it needs space. A thick fire in a long, narrow firebox would blow the fine coal right out the stack before it could burn. The draft was too heavy, the grate too small, the chunks too fine. Standard fireboxes of the era were long and narrow, fitted between the locomotive's driving wheels. They were designed for chunk coal, thick fires, heavy draft to keep them burning hot. Feed culm into one of those and you'd watch your fuel fly out the smokestack like confetti. But Wooten experimented. He tried burning culm in stationary boilers at Reading shops and stations, found that a thin fire, very low firing rate, wide grate, moderate draft, actually worked. The coal burned. Slow, steady, almost smokeless. The key was surface area. Spread the culm thin across a wide grate and let it smolder. The question everyone asked, could you put that in a locomotive? Could you mount a firebox wide enough to burn culm on a machine that had to move, had to generate power, had to fit through tunnels and around curves? In early 1877, Wooten patented his answer. The beast takes shape. Early 1877, Reading Railroad Shops, Reading, Pennsylvania. The first Camelback locomotive takes form under Wooten's supervision. It was a 460, a 10-wheeler configuration. 4 leading wheels, 6 driving wheels, no trailing wheels. Standard passenger locomotive arrangement for the era. But the firebox was massive, wide enough to burn culm efficiently. Too wide to fit between the locomotive's frames where fireboxes normally went. How wide? Wide enough that mounting it in the conventional location was impossible. The successful trailing truck design, wheels behind the drivers that could support a wide rear firebox, hadn't been perfected yet. That innovation wouldn't come for another 2 decades. So Wooten mounted his firebox above the driving wheels instead, right on top of the frames. Now came the problem no one had solved yet. Where do you put the crew? A conventional steam locomotive has the cab at the rear, behind the firebox. Engineer and fireman stand together, side by side. They communicate constantly, watch signals together. The fireman calls out landmarks on his side. The engineer responds. They coordinate every move. When something goes wrong, they both know instantly. But this firebox was so wide you couldn't see around it. Stand behind it in a conventional cab location and you'd be flying blind. The engineer wouldn't be able to see the track ahead, couldn't see signals, couldn't see grade crossings or switches or obstacles on the rails. The solution was brutal in its simplicity. Move the engineer forward, put his cab astride the boiler, straddling it like a saddle on a camel's back. Mount it in the middle of the locomotive, ahead of the firebox. From there, he could see forward clearly. And the fireman? Leave him in the rear. Someone had to feed the firebox. Someone had to shovel the coal. So the fireman stayed where he'd always been, at the back, near the tender where the fuel was stored, exposed to the weather, balancing on a moving platform while he shoveled, 20 feet from the engineer. Form followed function. The Camelback was born. They called it a Mother Hubbard, too, after the old Mother Hubbard nursery rhyme, because the cab sat on top like an old woman's cupboard perched above everything else. The first one worked. They fired it up, built pressure, and watched the steam gauge climb. The culm burned. The boiler generated steam. The pistons drove the rods. The wheels turned. The locomotive moved. Fuel cost savings, $2,000 a year per locomotive. That's roughly $30,000 in 1998 dollars, more than $50,000 in today's money. Per engine. The Reading ran hundreds of locomotives. The Reading built more. The design proved itself on test runs. Other railroads took notice. Central Railroad of New Jersey, Delaware, Lackawanna, and Western. Lehigh Valley, Baltimore and Ohio, Erie. Even roads as far west as Union Pacific and Santa Fe tried them. Before the Camelback, burning culm in a locomotive was impossible. After, it was routine. What took expensive coal now took waste. What cost money now made money. Railroads in anthracite country couldn't ignore economics like that. Public reaction? Mixed. When people saw their first Camelback, they stopped and stared. The thing looked wrong, unnatural. The cab sat in the middle like a tumor. The engineer rode high, alone, perched on top of the boiler. The fireman stood in the back like an afterthought, exposed to the elements. Newspapers covered the first test runs. Revolutionary design, read some headlines. Economical wonder, said others. The technical press praised Wooten's innovation, but the general public wasn't sure what to make of it. It looked dangerous. It looked wrong. But the first revenue runs silenced doubters. The locomotives moved freight and passengers. They pulled. They burned anthracite waste and did it nearly smokeless, perfect for passenger service. No coal smoke pouring into the cars, no soot settling on windows and clothing. Anthracite burned clean. Passengers noticed, Railroads advertised it. Railroads in anthracite country couldn't build them fast enough. Between 1877 and 1927, nearly 3,000 Camelback and Mother Hubbard type locomotives were constructed. Different wheel arrangements, different sizes. 040 switchers for yard work, 442 Atlantics for passenger service, 460 wheelers for mixed service, 280 consolidations for freight. But what nobody talked about yet, what wouldn't become obvious for years, was that they'd just split the crew in half and put the engineer directly above the machinery most likely to kill him. They'd isolated 2 men who needed to work as one, and they'd done it all to save money on coal. The beast worked, but it had teeth, gears that could crush bone. To understand what made the Camelback so dangerous, you need to understand what sat directly beneath the engineer's boots: side rods, crossheads, main rods, connecting rods, eccentric rods. All of it spinning, whirling, reciprocating, driving the locomotive forward at speeds up to 90 miles an hour. Exposed. Inches below the cab floor. The engineer sat on the right side of the boiler. A tiny cab, maybe 4 feet wide, maybe 5 feet long. Wood plank floor. The boiler passed through the center of the space, wrapped in lagging for insulation, but still radiating heat. In summer, engineers roasted. The cab was essentially a box, straddling a 400-degree cylinder. No airflow, no escape. Just you, the heat, and the constant vibration of 20 tons of machinery beneath you. In winter, the cab was a different kind of hell. The boiler kept you warm, too warm, but the sides of the cab were exposed. Wind cut through. Your front was burning from the boiler heat. Your back was freezing from the wind. And you couldn't leave, couldn't step out for relief. You were alone up there. The firebox behind you, the Wooten firebox, was huge. 82 square feet of grate area on some models. That's 3 times the grate area of a conventional anthracite locomotive. Compare that to a typical locomotive firebox of maybe 25 to 30 square feet. The difference was staggering. It needed to be that large because culm burns slow. Anthracite in general burns slower than bituminous coal. It's denser, harder, takes longer to combust, but it burns hotter and cleaner. Culm, being fragments and dust, needed even more surface area to generate equivalent heat. You couldn't stack it thick and expect it to burn efficiently. You had to spread it thin across a massive grate. Here's how the system worked, step by step. The fireman shoveled culm from the tender into the firebox through 2 firebox doors. The culm burned thin and wide across the 82-square-foot grate. The fire heated water in the boiler, hundreds of gallons of water at 200 psi on later models. The steam drove pistons in the cylinders, typically 20-inch or 22-inch diameter cylinders with 28-inch strokes. The pistons pushed rods. The main rods connected to the driving wheels via crank pins. The wheels turned. The locomotive moved. Simple, effective, brutal. But the context of impossibility here wasn't just the mechanism. It was the environment these machines worked in. Anthracite country, eastern Pennsylvania. The Reading Railroad hauled coal from mines to cities, Philadelphia, New York via Jersey City. The terrain was unforgiving. Grades that climbed and descended, sharp curves carved through mountain valleys. Weather that swung from summer heat that could kill a man to winter cold that froze your hands to whatever you touched. Summer temperatures in those cabs exceeded 130 degrees Fahrenheit. Engineers reported feeling faint. Heat stroke was a constant risk. Some engineers took to sitting on the windowsill, a dangerous practice, just to get airflow, to cool down enough to stay conscious. One Reading Railroad engineer fell out while doing exactly that. Tumbled off a passenger train at speed, survived with a broken leg, but only because he was lucky enough to fall clear of the tracks, and the coal itself, culm, was the original challenge. It was waste because it was hard to burn properly. The chunks were too small, sometimes just dust. The quality was inconsistent. Some batches burned hotter than others. Some had more slate mixed in. Some were dampened by rain before they reached the tender. You needed that massive firebox to make it work. And that massive firebox forced the engineer forward into the only place more dangerous than standing next to an open furnace, directly above the rods. The rods were the weakest link in the entire system. They had to handle immense stress. Every revolution, every stroke of the piston transferred thousands of pounds of force through those rods. Metal fatigue was inevitable. Worn bushings, the bearings that allowed the rods to rotate, would develop play, creating uneven stress. Poor lubrication would generate heat and friction. The rods would wear. Eventually, they would fail. And when a rod failed, when it snapped or broke free from its connection, it didn't just stop. It flailed. Picture a 6-foot piece of forged steel weighing hundreds of pounds, spinning at 60 miles an hour, suddenly breaking free from its mounting. The centrifugal force alone would swing it in an arc. The momentum would carry it upward, sideways, anywhere physics dictated, and if you were sitting in a cab directly above it, with only wooden planks between you and that flailing metal. The cab floor was wood, just planks, maybe 2 inches thick, no armor, no protection, no steel plating underneath. Wood was cheap, wood was light, wood was what they'd always used, and wood might as well have been paper when a broken rod came through. B&O crews called Camelbacks snappers. Not affectionately, not as a nickname, as a warning, because when a side rod snapped, it could punch through the cab floor and kill the engineer before he knew what hit him. The scale of these machines varied. Most were relatively small by later standards. 040 switchers weighing maybe 40 tons, 442 Atlantics around 150 tons, 460 10-wheelers in the 150 to 200-ton range. The largest were 30880 mallets built by Alco for the Erie Railroad in 1907, the only articulated Camelbacks ever made. Those were monsters. But size wasn't the danger. The danger was placement. Cost to build? The savings came not from construction, but from fuel. You could burn culm instead of quality anthracite. The locomotive design itself was actually more expensive. Custom cabs, modified frames, specialized controls, the need to separate systems between engineer and fireman. But the fuel savings justified it, for a while. The Reading Railroad alone operated hundreds of Camelbacks. The Central Railroad of New Jersey ran them extensively. The Lackawanna, the Lehigh Valley. These weren't experimental machines. These were mainline locomotives pulling passenger trains at 90 miles an hour on the Atlantic City line, pulling freight through mountain grades, switching cars in yards, and under every one of them the rods spun, waiting. The men who fed the fire, the fireman stood alone, no cab, just a short roof over the backhead of the firebox, a minimal shelter maybe 3 feet deep, open to the air on 3 sides. In winter, the wind cut through at 40 miles an hour, 50 if you were moving fast. In summer, the firebox radiated heat you could feel 10 feet away. Stand next to it for a shift and you'd lose pounds in sweat. And he shoveled. 4 tons of culm an hour on heavy runs, maybe more on steep grades when the engineer was pushing for power. Into a firebox wider than he was tall. 2 doors, one on each side of the enormous Wooten firebox. Had to feed both sides evenly, or the fire would burn uneven, and the steam pressure would drop, and the engineer 20 feet forward wouldn't know why until it was too late, and the locomotive started losing power. Every shovelful had to count. Culm wasn't forgiving. It burned thin. You couldn't just heap it in and forget about it. You had to spread it evenly across that 82-square-foot grate. Too much in one spot, and it would smother itself. Too little, and you'd have bare spots, cold spots, and your steam generation would drop, balancing on a moving platform while you worked. The locomotive swayed, rocked. hit rough track, and jolted sideways hard enough to throw you off your feet if you weren't ready. You learned to move with it, learned to time your shovel strokes to the rhythm of the rails, learned to brace yourself against the tender, against the firebox casing, against anything solid. Or you didn't last. The platform itself was typically a steel deck with minimal railing, just enough to keep you from falling off under normal circumstances. But normal circumstances were rare. Every curve, every switch, every rough patch of track. You were standing on a platform, moving at speed, holding a shovel, with an open firebox behind you radiating enough heat to cook you alive. Communication was impossible. The noise, the firebox roar, the wheels hammering on rails, the steam exhaust blasting from the cylinders, the wind, drowned out everything. You couldn't shout to the engineer, couldn't hear if he shouted back. 20 feet might as well have been 20 miles. Some roads ran a whistle signal line between the cabs, a series of coded blasts, 1 whistle for more steam, 2 for ease off, 3 for trouble. But mostly you were on your own, reading the fire, watching the water level in the gauge glass, watching the steam pressure, hoping the man up front knew what he was doing, hoping he'd give you warning before he needed full power. And there was the injector problem. In conventional locomotives, the engineer managed the injectors, devices that forced water from the tender into the boiler against the steam pressure. But on Camelbacks, the arrangement was different. The fireman sometimes had his own injector to manage, not always, but often enough. So you're shoveling coal at 4 tons an hour. You're watching the fire through 2 doors. You're monitoring steam pressure, and now you're operating a lifting injector that's temperamental on a good day, that requires careful manipulation of valves, that will airlock if you let the water level drop too low, or flood if you open it too far. Maintenance nightmares were constant. Bearings had to be greased every 6 hours, by hand, while the machine was running. You'd lean out with a grease gun, trying to reach the bearing cups on the side rods, on the crossheads, on every moving joint, trying not to fall under the wheels, trying not to get caught by the rods as they spun past. One slip, one moment of inattention, and you'd be under the wheels or pulled into the machinery. It happened. Not often, but often enough that every fireman knew someone who'd lost a hand, lost an arm, lost their life reaching for a bearing that needed grease. Operators gave them names. Mother Hubbards was the most common. It stuck, became almost official. But some names were darker. The Widowmaker, Death Trap, the Snapper, as the B&O crews called them. Men didn't refuse to work them. Jobs were jobs, and railroad work paid better than most, but everyone knew the risks. The experienced firemen developed a 6th sense. They could feel when something was wrong up front, even though they couldn't see the engineer. Could sense when the locomotive's rhythm changed, when the throttle response wasn't right, when the engineer should have signaled but didn't. One story survives from the Reading Railroad. An engineer sitting on the windowsill of his cab, a common practice among Camelback engineers to get airflow, to cool down from the boiler heat, fell out while running a passenger train, tumbled off at speed, hit the ground, rolled into the ballast beside the tracks. The fireman didn't notice. He was 20 feet back, deep into a shift, dealing with flue leaks in the firebox, leaks that were spraying water and dropping steam pressure, and trying to keep the pressure up by firing harder. The train ran past 2 stops before the conductor walked forward and pulled the emergency brake cord. They found the engineer miles back along the track. Broken leg, cuts and bruises. But alive, otherwise okay. Lucky beyond measure. In another incident, better documented, an engineer died at the controls. Heart attack, most likely. Maybe heat stroke, maybe just exhaustion and stress. The train, freight probably, given how long it took before anyone noticed, kept running until it stalled on a grade leading into a tunnel. The fireman kept shoveling, kept watching his gauges, wondered why they were slowing down, why the engineer wasn't giving him signals, why the throttle seemed wrong. But the locomotive was still moving, still pulling. The engineer must know what he's doing, must have a reason. Didn't know the engineer was dead until the train finally stopped. That was the nightmare of the Camelback, the thing that kept experienced railroaders awake. One man could die, and the other wouldn't notice until the train stopped moving. No way to check, no way to see, just 20 feet of boiler and machinery between you, and the roar of the rails drowning out everything else. When the steel screamed, the near misses came first. They always do. Small incidents, warning signs that something fundamental was wrong with the design. A cable snapped on a Jersey Central locomotive, whipped through the air, missed an engineer's head by inches, left a groove in the wooden cab wall where it struck. The engineer felt the wind of its passing, knew he'd just survived by luck, not skill. A crosshead came loose on a ridding locomotive. The bolt that held it to the piston rod worked free under vibration. The crosshead banged against the cab floor, left a dent in the wood planking. Left a dent, but didn't break through. The engineer felt the impact, felt the locomotive lurch, shut down just in time before the whole assembly tore free. An engineer on a Lackawanna locomotive felt the machine lurch sideways, heard a grinding sound beneath him. Metal on metal, wrong somehow. Shut down immediately. Inspection found a main rod bearing with almost no metal left. Another 100 miles and it would have seized completely, probably torn the rod free, probably killed him. These were warnings, small ones, close calls, things that should have prompted immediate design changes, immediate retrofits, immediate recognition that putting men above exposed machinery was fundamentally unsafe. They didn't. Railroad management saw the warnings. Engineers reported them. Firemen reported them. Union representatives pushed for changes, but the economics were too good. Camelbacks saved too much money on fuel. And the accidents, the near misses, could be blamed on maintenance, on operator error, on bad luck, not on the design itself. Then came the breaking point. The exact details of specific fatal accidents are sparse in the historical record. Railroads didn't advertise when their equipment killed people. Newspapers reported some incidents, but not systematically. Safety reports weren't standardized. OSHA didn't exist. The Interstate Commerce Commission gathered some data, but not comprehensively. But the pattern is clear. Engineers died, multiple times, across multiple railroads. On more than one occasion, documented by the B&O Railroad Museum itself, a Camelback engineer perished in the cab while the oblivious fireman continued to stoke the fire. The B&O Railroad Museum documentation is explicit. Engineers were mortally wounded when driving rods broke beneath the cab. The rod would snap under stress. Metal fatigue, worn bearing, poor lubrication, whatever the cause, and flail upward. The broken end would punch through the wooden floor, impact the engineer, kill him instantly or leave him dying alone in his cab. No warning, no time to react, just sudden catastrophic failure. 1 second you're running at speed, watching the track, feeling the vibration of healthy machinery beneath you. The next second there's an explosion of splinters and screaming metal and pain. The fireman, 20 feet back, heard nothing unusual over the roar of the fire and the noise of the rails. The sounds of the locomotive, always loud, always violent, masked everything, kept shoveling, kept watching his gauges. Maybe noticed the locomotive was slowing, maybe wondered why, but no alarm, no signal, no way to know. By the time anyone realized what happened, it was too late. The engineer was dead. The fireman had been working beside a corpse for miles and didn't know. The human cost accumulated. Engineers killed by broken rods, multiple confirmed cases, exact numbers lost to history. Engineers who died from heat stroke in summer, working above a boiler that turned the cab into an oven, at least a handful of documented cases. Firemen who fell from their exposed platform, crushed beneath the wheels or dragged under. Again, multiple incidents across multiple roads. Firemen who froze in winter, unable to maintain their footing on ice-slicked metal, unable to work effectively with frozen hands, developed frostbite, lost fingers, sometimes lost their lives when they slipped and fell between locomotive and tender. There are reports, documented in Union records and newspaper accounts, of engineers and firemen alike succumbing to the grueling conditions, heart attacks from the heat and stress, heart attacks from the physical demands, accidents from the isolation and inability to communicate, deaths that could have been prevented if the two men had been in the same cab, where one could see the other collapse, where one could signal for help, where one could stop the train immediately. The newspapers noticed. When a Camelback was involved in an accident, especially a fatal one, the design made headlines. Dangerous locomotive claims. Another life, read one headline. Mother Hubbard death trap, read another. Public outcry grew. Citizens wrote letters to editors. Railroad workers, through unions like the Brotherhood of Locomotive Engineers, started pushing back harder. This design was a death trap. Everyone knew it. Labor unions lobbied for change. The Brotherhood pointed to the death toll, pointed to the near misses, pointed to the fundamental unsafeness of separating the crew, of perching the engineer above the rods, of exposing the fireman to the elements. They demanded end cab conversions, demanded safety modifications, demanded recognition that economics shouldn't override human life. By 1918, the Interstate Commerce Commission had seen enough. According to widespread historical accounts, they banned further construction of new Camelback locomotives, allowed a few exceptions, engines already under construction, contracts already signed, but the message was clear. No more. In 1927, the ICC reportedly went further. No more new orders, no more rebuilds. The center cab locomotive was officially deemed too dangerous to continue. Existing Camelbacks could remain in service. They were grandfathered in, but no new ones would be built. But here's the thing. Many sources claim this ban. Virtually every article, every museum description, every historical account repeats it. But extensive research has found no actual ICC order in 1918 or 1927 explicitly banning Camelbacks by name. No regulation number, no documented decree, no official prohibition in the ICC records. What's clear is that railroads stopped building them anyway. Safety concerns, union pressure, economic factors, public opinion. All of it combined to kill the design more effectively than any government mandate could have. What really killed the Camelback was technology. Around 1910, mechanical stokers became reliable. These devices, powered by small steam engines, automatically fed coal from the tender into the firebox, evenly distributed across the grate. You didn't need a fireman standing in the back manually shoveling anymore. The stoker did the work, and mechanical stokers could handle small coal just fine, could handle culm, could burn it in a more conventional firebox arrangement. The wide Wooten firebox was no longer necessary. At the same time, trailing trucks, wheels behind the driving wheels, were perfected. The radial trailing truck, developed in the early 1900s, could support a large firebox mounted at the rear of the locomotive, behind the drivers, and still maintain proper weight distribution and tracking on curves. Now you could mount a large firebox at the rear of the locomotive, behind the drivers, with a conventional cab. The engineer could sit in a normal position, see forward clearly, and have the fireman right next to him. Communication restored, safety restored, crew coordination restored. The Camelback's sole advantage, the ability to burn cheap culm in an era before mechanical stokers and trailing trucks, evaporated. And when culm prices rose after 1908 due to industrial demand for stoker-fed boilers in factories, the economic case collapsed entirely. Culm was no longer worthless waste. It had value, it cost money. The savings diminished. The last new Camelback was built by Baldwin Locomotive Works for the Lehigh and New England Railroad in 1927. After that, the design was dead. Some railroads converted existing Camelbacks to end-cab configurations, moved the engineer back to a conventional position, modified the boiler and firebox arrangement. The Erie Railroad converted their three massive 0880 mallets to two 882 end cab locomotives, but mostly the Camelbacks just faded away, scrapped, retired, replaced by conventional locomotives that didn't kill their crews, where titans go to die. What did the Camelback accomplish? It proved you could burn waste coal. It moved passengers and freight across eastern Pennsylvania for 50 years, from 1877 to 1927, half a century of service. It saved railroads millions in fuel costs during the era when anthracite was plentiful and coal was worthless. Millions of dollars, millions of tons of waste turned into useful fuel. It helped build the coal-hauling railroads that powered American industry. The Reading, the Jersey Central, the Lackawanna, the Lehigh Valley. These lines moved anthracite from mines to cities, heated homes, powered factories, enabled industrial growth. The Camelback made that economically viable, made it profitable, made it possible to expand service, build new lines, compete with other roads. The passenger service advantages were real. Anthracite burned clean, almost smokeless, perfect for passenger trains. No coal smoke pouring through open windows into the cars, no soot settling on clothing and faces, no passengers arriving at their destination covered in grime. Railroads advertised it. Clean coal comfort, read the ads. Smokeless service. But it came at a cost. How many engineers died? The exact number is lost to history. Railroad records were incomplete. Safety reporting was inconsistent. Deaths were often attributed to accidents, without specifics. But the phrase, on more than one occasion, appears in multiple sources. Multiple occasions, multiple deaths, multiple engineers who died alone while their firemen kept working, unaware. How many firemen froze or fell or burned? We don't know. How many men lost fingers, lost hands, lost limbs, reaching for bearings while the machine was running? How many heart attacks? How many heat strokes? How many men broken by the work? What we know is that on more than one occasion, a man died alone in his cab while his partner, 20 feet away, kept working. We know that B&O crews called them snappers, and everyone understood why. We know that the design was eventually abandoned not because it didn't work, but because it worked too well and killed too many people. By the 1950s, most Camelbacks were gone, scrapped for metal during World War II, converted to end cab configurations, replaced by diesels that didn't need fireboxes at all. The Central Railroad of New Jersey operated the last ones in revenue service, finally retiring them in 1954. A single 040 Camelback switcher survived in industrial service at a coking plant, the E&G Brook Iron Company in Birdsboro, Pennsylvania, until the early 1960s. It worked switching cars in the plant yard, the last of its kind to turn a wheel under steam. When it finally stopped running, an era ended. Today, 5 Camelback locomotives survive. All in museums, none operational. None will ever run again. They're too dangerous, too unique, too historically significant to risk. CNJ number 592, a 442 Atlantic, sits in the Baltimore and Ohio Railroad Museum in Baltimore, Maryland. The world's only surviving Atlantic Camelback, built in 1901 by the American Locomotive Company, could hit 90 miles an hour on the Atlantic City line, pulled passenger trains in style and speed. Now it sits silent, restored, beautiful, dead. B&O, number 173, a 460 10-wheeler, is at the National Museum of Transportation in St. Louis, Missouri, built in 1876, one of the earlier Wooten firebox designs, though technically a precursor camel type rather than a true Camelback. Still dangerous, still separated the crew. B&O number 305, another precursor camel type from 1869, also resides at the B&O Museum. Even earlier design, long cab that sat atop the boiler. Same fundamental problem, crew isolation. Delaware, Lackawanna, and Western number 952, a 280 consolidation built in 1905, is at the Museum of Transportation in St. Louis. One of the Lackawanna's workhorses, pulled freight through mountain grades for decades. And reading? Number 1187, a tiny 040 switcher built in 1903 by Baldwin, was purchased by the Age of Steam Roundhouse Museum in Ohio in 2020. It's undergoing cosmetic restoration. The wooden cab rotted away during years of outdoor storage at the Strasburg Railroad. They're rebuilding it from original Baldwin drawings. When finished, it'll look like it did in 1903. But it will never move again. These 5 machines are monuments, not to progress, not to innovation, to compromise. Railroads needed cheap fuel. Engineers designed a solution. It worked. It saved money. It proved the concept. It enabled growth. And it killed men. We look at those 5 survivors in their museums and see history, unique engineering, a footnote in the evolution of steam power. Visitors photograph them. Children climb on the walkways. Placards explain the Wooten firebox and the cab placement and the economic advantages, but they're not footnotes. They're testaments to what happens when economics overrides safety, when the cost of fuel matters more than the cost of lives, when everyone knows something is wrong. The engineers know, the firemen know, the unions know, the public knows, but the money is too good to stop. The Camelback didn't fail because it didn't work. It worked perfectly. That was the problem. It worked so well, saved so much money, proved so economically viable, that railroads kept building them for 50 years, kept ordering them from Baldwin and Alco, kept putting men in those separated cabs even though everyone, from the engineers to the firemen to the public, knew they were death traps. Nearly 3,000 were built. 50 years of service, millions in fuel savings, and a death toll that was never properly counted because it didn't have to be. Progress has a price. The men who rode 20 feet apart, unable to hear each other scream, unable to save each other when the iron beneath them failed, they paid it in full. They paid it in blood and broken bodies and lives cut short. They paid it alone in their cabs, dying while their partners worked on, unaware. They don't make them like that anymore. Not the machines, and not the men who rode them knowing the risks, knowing the odds, knowing that every shift could be the one where the rod snapped and came through the floor. 5 survivors remain, silent witnesses to an era when cheap coal mattered more than human life, when innovation and economics and pure engineering brilliance created a machine that worked perfectly and killed indiscriminately. The Camelback locomotive, 20 feet of steel between life and death, a masterpiece of compromise, a monument to the cost of progress.